Hello, everyone. Today we are going to talk about image segmentation, and we are going to continue on more techniques for image segmentation. In particular, today we are going to talk about edge detection. So edge detection is basically one of the techniques for segmentation. And segmentation, if you recall, it was our way of segmenting foreground objects or outlining foreground objects from backgrounds. Most algorithms are based on discontinuity and similarity of intensity values within an image. We talked about morphology, which is the first technique that we talked about here, and that just uses the shape or texture of region to be able to segment it from the image, so either to keep it or remove it. For example, the structuring elements, if it fits within a certain shape, then based on dilation or erosion, then you can keep it or remove it. Last time we talked about also thresholding, which is identifying regions based on their pixel intensity. So that's just purely the pixel intensity. If a certain pixel has a certain value, if it's above a certain threshold, then it becomes a foreground. If it's below that threshold value, becomes a background. And today we're going to talk about edge detection as another way for segmentation to find the foreground objects. Now we're going to talk how this is done, and if you recall, we have some discussion about image derivatives in one lecture before, and we talked and we said there is first order derivatives and second order derivatives, and basically they find discontinuities or sharp changes in pixel intensities. And these are basically what edges are. They are extreme changes or large changes in pixel intensities. Just double checking that the audio is working. That's good. So next class, we are going to talk about parametric edge description, and that's half transform. And we're going to talk about that next class. But for today, we're going to talk about, in particular, Laplacian of Gaussian, difference of Gaussian, and canny edge detectors. We've heard about Roberts and Sobel before, but we're just going to go over and just do a quick overview of these ones before we go into the new ones. So edges in general are representation of boundaries of foreground objects or between objects in general. If you look at the room that you're sitting in right now, and you try to look at any edge that you see, you will see there is a change in color between any two regions, and that's what distinguish an edge to be there. There is true edges that represent true and actual boundaries, and there is false edges that are not really edges, and these are due to illumination effects such as shadows and so on. If we look at over here, we can look at this image and perform edge detection, and you see there is right away you will find the edges of all the objects in the image. It looks as easy, but really it's not. If we have the same image and we just have non-uniform illumination over it, then basically what happens is that you will see that you will lose a lot of the details, and then, for example, over here versus over here, and then the edges over here, that's completely lost, and so on. So this is not as easy as it looks like. Moreover, it's not only missing edges, you will see false edges to start to appear, which is you will see as this edge over here that represents this shadow, and edges over here. If you recall in the first lecture that we did together, I showed you one of the projects that I worked with for the city of Calgary Traffic Management Center, where they were doing automatic monitoring for the highways, Trans-Canada Highway 1 in particular. And one of the big issues that they were having with the system that they purchased for millions of dollars is that it's generating too many false alarms. And these false alarms are, a lot of them were caused by just shadows on the streets. And in my work over there, we worked on algorithms that we can detect and filter out shadows and remove them from the actual images. And later on, actually, we patented that work. We patented that work, and I got my first patent out of it. So let's look at some of the examples as we see here for a picture of a tree. If we look at this tree and we apply edge detection with certain parameters, we can detect all the edges over there. You will see this image, and then maybe someone will come and say, I only want to see the main edges of the image and the tree, and then we will get this image here. There is different models for edges, as we've seen before. There is a step edge where you have a sharp and well localized transition in intensity. So that's black, and then in 1 pixel here, and then that's white. So that's a step ideal edge. Or you can see ramp, and we see a lot of them. Most of edges will be ramp edges. So there is a gradual change in intensity. And there is a roof, and the roof just gets 1 intensity, and then there is a sharp transition going up and then down and then to the back again. If you look at this MRI, we will see that there is different models as we've seen and talked about. So over here, you will see that's my roof, and then you will see that's almost coming as an ideal, but that's like only 2 pixels, whereas this here spans 9 pixels. So both of these, they can be categorized as ramp, but this is very close to be an ideal edge, which is a step. We've talked before about detecting edges using image derivatives, and we talked about how we can do that using first derivatives and second derivatives. So I'm just gonna refresh your mind. In the first derivative, we just differentiate in the x direction and then differentiate in the y direction. So for differentiating in the x direction, it's f of x plus 1 and y minus f of x, and that can be represented with a mask of +1 and -1. Remember, we're going x direction is this way and y direction is in this way. And then again, if this is the pixel of interest, then we can apply a mask where we have 1 at f of x and y plus 1 and -1 at f of x and y. The second derivative can be looked at using f of x plus 1 plus f of x minus 1 minus 2 times the current pixels. So you add the one before, the one after, minus 2 multiplied by the intensity of the pixel, and the same in the y direction. This is the example that we've seen before, and that's very closer to what we have seen in the midterm. What's really interesting that we want to talk about is the effect or detecting first derivatives and second derivatives. So in first derivatives, there is always a production of thick edges, and we talked briefly about that, and we discussed it in class last few times. And the first derivative will be positive when the values goes from dark to light. So from going from dark to light, that will produce a positive value, or it produces a negative value if it's the other way around. In the second derivative, remember, the second derivative doesn't produce value in constant change. So it produces values on the onset and the offset. So what we need to do is we need to detect that zero crossing over here. Okay. And once I detect that zero crossing, then the center becomes that is the edge. Okay. We need to also to consider the effect of noise when we talk about edge detection. In this example over here, if I have, this is my original image or my original edge, and it's just a ramp edge. So if you see, that's just a ramp edge like this. And then if I look at the first derivative and the second derivative for each one of them, let's look at the effect of noise. If I have this different 3 samples of the original edge, the first one has no noise, so I added a noise over on all 3. But the first one, Gaussian noise standard deviation is 0. The first one is standard deviation is 1. The second is a standard deviation of 2. So if I take the intensity, just looking at the intensity profile over here, okay, and then over here, and then over here, and then over here. So you see there is the effect of the noise is evident as we go and start adding the noise to the image. If I start looking at this over here, so that's again, that's the origin. So that's pure, there is no noise here completely. That's basically my intensity profile. That's the first derivative, and that's the second derivative. Okay. If I add a Gaussian noise with a standard deviation of 0, so you'll see even with noise with this Gaussian noise with standard deviation of 0, you will see that there is going to be starting to have a bit of a noise over here. There is still very obvious zero crossing, and we can get rid of that with some probably thresholding. If we have the image corrupted by Gaussian noise with standard deviation of 1, and we look at the intensity profile, the noise becomes more clearer over here. Look at the first derivative, how it's looking at, and then we look at the second derivative. Now we started to see that the first and the second derivative are very, very hard to work with. Now, if we add with a standard a Gaussian noise with standard deviation of 10, then now this is really, really noisy image, and really you can't do edge detection on that. So typically in any edge detection operation, the first thing that you want to do before you start very first step is you need to smooth the image. So that's very important, as we've seen from this example, because it smooths the image and tries to get rid of the noise. So it suppresses the noise and try to remove that. The second thing is we need to detect the edge points, okay? And then we need to do edge localization, which is try to make sure that these edge points are in its true location. So these are really edge points. So we talked about the basic technique before, so the image gradient. Okay, and so I'm not gonna go over that. I'm just gonna go very, very quickly just to remind you of that. And then we're gonna talk about the advanced technique, which is the Laplacian of Gaussian and the canny edge detection. So the basic edge detector, we talked about image gradient. So just to remind you, we can apply an image gradient at any pixel, and the image gradient basically is the vector that has a gx and a gy. What is gx? That's the, for example, the first derivative in the x direction of Sobel or of any first order derivative, and the gy is the first derivative in the y direction. So it's partial f by partial x and partial f by partial y. In a lot of application, we use Sobel. There is another one that we don't study in the course, which is called Susan. Also is very famous and used very commonly in the industry. Okay, we take the gx and the gy, and then we can calculate the magnitude at the direction. And the magnitude of the gradient is basically the square root of gx square plus gy square, and then the direction is the tan minus 1 gy over gx. The result is following. The result, if we apply that gradient, image gradient at this pixel over here, it will give me a vector. Now this vector will have a strength, and that strength is represented by m, and it represents the strength of this edge point. If it's like really high, then this is a very strong edge point. Okay? And the second thing is the direction. So the direction of the gradient vector. Now the direction at alpha angle, see that's alpha angle. This alpha angle is basically representing the normal to the edge direction. So that alpha that you calculate over here, that presents a normal to the edge direction if there is an edge over here. Okay. As we said, we can use the gx and the gy. We can use Sobel operation, and we have the gx and the gy in Sobel. If we look at just for example, going in the y direction, so detecting an edge in the y direction, so that's going to be like an edge this way. It's like going to be a vertical edge. So there is a change from here to here. This filter over here can be decomposed in the product of this mask convolved with this mask. But why do we want to do that? Because we just want to say that the Sobel is a combination of an averaging and a differentiation kernel. This is the differentiation kernel that you're familiar with, from +1, 0, -1. So it's just going from one value over the pixel of interest to the other one. And it sums to 0. And then this is basically by smoothing or averaging filter. Let's just look at some examples of finding the gradient image using the Sobel as the gx and the gy. So if this is my original image and I'm applying the gx, now I'm going to just use the absolute value of gx because I don't care if it's negative or positive. I just care that there is an edge point or not. So that's going to be gx. Okay, so as you see here, it's very clear that we want to find the horizontal edges. So you see these horizontal edges over here, all the horizontal edges are very, very strong. They are white. Okay. And then if we want to do the GY, so we want to go from this intensity to this intensity. So it means that we need to detect vertical images and edges in here. So basically we'll see that these are the edges that are being detected. And then if I do the square root of gx square plus gy square, this is equivalent or can be approximated by adding the absolute value of gx plus the absolute value of gy. Some textbook will use this notation for m. So that's basically m. So basically it will give you all the edges in the image. Now, if you look at this image here, we'll see there is some edges here that are happening, and these are like unwanted edges. So how do we do about them? As we said, we can apply smoothing. And then, moreover, we can apply a threshold to remove weak edges. Let's look at this image here. So we will have the same thing, okay? But here we will apply first a smoothing filter using a 5x5 averaging filter prior to edge detection. So that's a strong averaging filter, 5x5. So it smooths it. And then when we apply it, you will see that we got rid from a lot of the noise that were happening over here. And then if we add gx plus gy, we get a cleaner version of this image. You see this here? You see all that's happening here? Much cleaner. Okay. We can also detect diagonal edges. So we want to add diagonal edges. So we're gonna add the diagonal filters for Sobel. And then the last step, as we said, we can take the image that's output, and then we apply a thresholding operation to it, and the thresholding operation will be able to remove a lot of the noise. So over here is the original image, and then over here, that's going to be a thresholded version with a threshold selected to be 33, the highest value. Here, if we take the diagonal images as well. Okay. In MATLAB, as we said, we can use just the MATLAB command called edge, and then we can just pass to it what type of operator we are using, so Sobel or Roberts or Pruitt, and that will give me the different thing. You will notice with the basic edge detection, probably Sobel is the best one that performs or give you good results. Okay, so that's just quick revision, and we've talked a lot of this in the previous class. Now we want to talk about a bit more advanced edge detection techniques. So the first one we're going to talk about is called the Marr-Hildreth edge detection. The Marr-Hildreth edge detection is basically an edge detector that uses the Laplacian of Gaussian. And in real application, it uses the difference of Gaussian as an approximation for the Laplacian of Gaussian. So that's my Laplacian of Gaussian, and then this Laplacian of Gaussian is approximated using the difference of Gaussian. So the idea, we need to detect certain edges based on their scale, so for segmentation. So if I have, this is my image, and then I want to detect all the small edges and the big edges, I will get something like this. But I can apply the Marr-Hildreth edge detector, and then it will only detect the strong edges that are, you see over here, which is really a good representation of this image here. Okay, so what's the basic step in the Marr-Hildreth edge detector? We convolve the image with a Laplacian of Gaussian filter, and then detect the edges that go through the Laplacian of Gaussian by detecting the zero crossing. So if I have, this is a ramp edge, for example, I apply the Laplacian of Gaussian, which is a second order image derivative, and that will give me these two responses here. And then basically what happens is that I detect the zero crossing here, and that becomes the center of this thick edge. If I apply a first order derivative, if you recall, this will give me all as edge points. But really, I'm only interested in just zero crossing. So instead of, if you recall, when we were talking about Laplacian of Gaussian as a second order derivative, we said it will provide with you a double edge, right? So one here and one here. In the Marr-Hildreth, it detects the zero crossing to get just that one pixel in the middle. The idea behind using the Laplacian of Gaussian is that the Laplacian is the second order derivative as we have seen it before. Okay, and then the Gaussian, so we said Laplacian of Gaussian, and the Gaussian is a strong filter that we can use with certain sigma to smooth the image and only keep strong edges determined by the scale of the sigma in the Laplacian in the Gaussian filter that we are using. Okay. In practice, we don't really apply the Laplacian of Gaussian. We apply the difference of Gaussian, which is a good approximation of the Laplacian of Gaussian. Okay, let's look at applying Laplacian of Gaussian filter with a small sigma and with a large sigma. So if I apply a Laplacian of Gaussian with a small sigma, then I will get a lot of details. But if I have a lot of edges, if I apply it with a large sigma, then it will just be only the strong edges here. Just for your reference, in this image, we have the gray here to be zero value, the black is negative value, and the white is positive value. In Marr-Hildreth edge detector, after you find this image, then you perform the zero crossing to find the edges. Okay, so the Laplacian of Gaussian, as we said, we look at it, and it's just basically a Gaussian filter, and then we apply the Laplacian operator to it, which is the second derivative of the Gaussian filter. So basically, the Laplacian of Gaussian is this function over here, okay, for any point at x and y. Just for your knowledge, it's called also the Mexican hat operator, just because how it represents how it looks like. You see how it looks like? That's just the Laplacian of Gaussian. Now, to be fair, this is actually the negative or upside down Laplacian of Gaussian. Okay. Let's look at the Laplacian of Gaussian, how it looks like. As we said, this is a 3D operator. That's just basically going to be the plus. So if we look at it, so until here, that's the positive values. And then over here, which is the outer here side, that's the negative values. So you see that's going to be just basically the Laplacian of Gaussian. Again, I'm saying that's the Laplacian of Gaussian just to be technically correct. That's the negative of the Laplacian of Gaussian. Okay. This is just if we try to represent it using an image, okay, and then that's the discrete approximation of that Laplacian of Gaussian using a 5x5 mask. If you recall, in differentiation or differentiative filters, we have to have the sums always must sum to 0. So in areas of constant intensity, these must be, if all the image has, like, let's say intensity 10, so we need to multiply this by all beyond the 10, so it will just give us a 0. Okay, here is an application for an image and then applying a Laplacian of Gaussian, and that's just show you how it will look like if I want to go, if this is just a small representation of one edge that's coming here, then the Laplacian of Gaussian will give me this, and then it will give me this. Okay. Okay, so the Marr-Hildreth algorithm. As we said, we need to take the Laplacian of Gaussian and convolve it with the image f of x. But since this is a linear process, there is an easier way to do it. So first we apply or convolve the Gaussian filter with the image and then take the Laplacian or the second order derivative for it. So the steps are as follows. First, we filter with a Gaussian filter. Okay, now that Gaussian filter will be of size n to n, where n is the smallest odd number greater than 6 sigma. Why did we choose 6 sigma? Because 6 sigma will make sure that 99 point something of the information is enclosed within the envelope. Okay. And then we compute the Laplacian for this image, and then the last step is to find the zero crossing of the image from this step here to eliminate the double edges. So how do we find the zero crossing at any pixel? Basically, a zero crossing means that two opposing pixels are different. So up and down pixels, right and left pixels, or two diagonal pixels will produce opposite signs. So 1 plus 1 negative. Once I do that, I will find the zero crossing between them. Okay. Let's look at just an image here to show you the Marr-Hildreth technique to detect edges. If I have this as my original image over here, and then I just apply the steps here, filter the image with a Gaussian, and then compute the Laplacian, that will give me this image over here. Now I want to detect zero crossing because I need edges, and we said, so we will examine pixels. If I have a pixel, I will look at opposite sides, up and down, right and left, and then the diagonal. If there is opposite sign, then basically that's an edge point. Okay. So if I use this technique, that's what I will get over here. Okay. So this is the spaghetti effect. And that's very common if you're trying to use the Marr-Hildreth technique raw without any extra steps. The typical step that's always added with the Marr-Hildreth technique is to use thresholding. So we look at the different values that are produced over here, and then we say that we need to take a threshold of zero crossing using a threshold of 4% of the maximum value. So we find the maximum value, we find what's 4%, and that becomes my threshold. And then we look at the different points over here, and then we eliminate anything that's below 4%, and then we will get this much cleaner image. As you see, it's thin edges, it's not double edges as we've seen with the Laplacian of Gaussian as a second derivative by itself. It's very nice, very clean, contains all the details that I really want. Let's look at just a demonstration to see how this works on one edge. So we're looking at this edge here, and then we're gonna look at over here. So this is step 1 and step 2 before doing the zero crossing detection. So at the very beginning, so that's just after applying the Gaussian filter at the very beginning. So now we have, that's my Laplacian of Gaussian. We have a plus and the negative to represent, if you recall, this here, the Laplacian of Gaussian. In real application, when we are using it, the inner is negative and the outside is the positive, versus the illustration that I have showed you here. I was showing you this here. I said this is positive and that's negative, and that's because that's the positive part, so that's this. Then the outer side is the negative one, and I said this is the negative of the Laplacian of Gaussian. In real, we use the actual Laplacian of Gaussian, which is negative in the inside and then positive on the outside. That's the actual Laplacian of Gaussian. So that's why, just to explain this point. So at the very beginning, this is an area of a constant intensity at this pixel here. So all the sums here to be 0. So it's just gonna produce 0. Recall the gray is 0. So that's why in this area here, it's gonna be 0. And then as I detecting all the pixels, investigating all the pixels as they are edge points or not, then I come to this point over here, and then you will see now that the positive is less and the negative is more. So that means that the output is negative in the image. Okay. Why the positive is more? Because the underneath here, that's just dark, so that's gonna be like giving small values over here. Okay, and basically that becomes a higher value. Okay, and then as it moves over here, the positive and the negative areas of the Laplacian of Gaussian are basically the same again, so its output is 0, and that's the zero crossing that we were looking for. And then if we go over here again, then that becomes positive in the edge image, and then if I go over here, that becomes 0. So it becomes like almost like it's 0 and then negative and then 0 again and then positive again, and then so that's the point that I'm looking for. Okay, so this here is just an illustration of this different clicks that I just explained. What's the benefits of the Laplacian of Gaussian? Because it has a Gaussian operator, so it reduces the noise effect. Okay, it's a second order and isotropic. So in terms of rotation, so basically I don't have to apply a certain filter in the X direction and another one in the Y direction. It's basically gonna work in X and Y directions, and will produce thin red edges rather than thick edges as opposed to the first order derivatives. As we said, in MATLAB, actually MATLAB doesn't use the Laplacian of Gaussian. It uses the difference of Gaussian. What is the difference of Gaussian? It's basically an approximation of the Laplacian of Gaussian. So that's my Laplacian of Gaussian. And then the DOG is just an approximation using the Gaussian with sigma 1 minus the Gaussian with sigma 2. The condition here is that sigma 1 over sigma 2 have a ratio of close to 1.6. Let's look at MATLAB. So I can say edge, and I just say with Laplacian of Gaussian, and then I pass the different sigma. So if this is my edge image, and I'm applying the Laplacian of Gaussian edge detector, then it will just give me the difference detection. As you see, as the sigma grows, only strong edges will survive the smoothing operation, and then it will be detected. Okay. What's the problem with the Laplacian of Gaussian? The problem is that when you are using Laplacian of Gaussian and you are start to apply it here, as you seen, if it's over here, then basically it's going to detect this edge point, which is going to be working fine. But as you move towards the corner, pieces of this here will catch this edge as well. So it will start to produce a response to the vertical edge closer to the corner. So the output will be always having this bumpy shape. Okay. If I have sigma to be 3 and I apply Laplacian of Gaussian on this image, you will see the bump will just start to occur as it gets closer to the edge. And since sigma is small, then this Laplacian of Gaussian is small, so it will only appear at the very end. If you have a sigma to be 10, so that's going to be a big Laplacian of Gaussian, so it starts to appear early. So when you are here, it starts to catch part of this and then starts to produce this effect. Okay. The second technique that we are going to talk about is called the Canny edge detector. And that's one of the edge detection techniques, 1986. It's the best so far, and it's very commonly used in edge detection, especially the ones that are corrupted by white noise. Canny, who's the author of this paper, he had 3 objectives when he was looking at coming up with a new edge detector. He said, I want to have a low error rate, which means that I want to minimize false edges as much as I can. And I need my edges to be very well localized, which means that the edge points need to be true and close to the actual edges as much as possible. And I want to have a single edge response. Instead of having thick edges, I just need to have one edge, 1 pixel edges. So in doing so, he came up with using the first derivative of a Gaussian filtered image. So the first step is to smooth the input image with a Gaussian filter. And then the second step, compute the gradient, magnitude, and angle images. And then the third step is apply non-maxima suppression to the gradient magnitude image. And then use double thresholding, or they call it hysteresis thresholding, to link edges together. Let's look at them one by one. First step. First step is smooth the input image with a Gaussian filter. Now you're all expert, you know what's a Gaussian filter, and you know what do we need to do to suppress the image, noise in the image, and so on. So what we will do, we'll take the input image and then apply that Gaussian filter to it. Okay. Second step, compute the gradient image. And again, you can just use the Sobel, the Roberts, whatever. Usually we use the Sobel in this step. So we'll just go and say, that's my Gaussian smooth image. And then that will produce to me the gradient magnitude and the gradient angle images. Okay, and then apply non-maxima suppression on the gradient magnitude image. What does that? So the gradient magnitude image is values in each pixel that represents the potential edge points and their values. What it does, it uses something called non-maxima suppression, which is a thinning technique. If I have this as the pixel, and then let's say we have 4 directions, 1, 2, 3, 4. That's the basic edge directions that this pixel can be on. And then what it will do is find the direction from one of these 4 that we have that's normal to the edge. So find the direction that is closer to the alpha angle. What is the alpha angle? It is over here. So if I have a pixel, and that pixel, I will find what's the value of the alpha over here. And then what I will do is find the direction that's very close to this alpha. Okay. And then what I will do is look at the 2 pixels in the alpha direction. And I will ask this question. Is this point, the M value of this point, is greater than these 2, the M value of these 2? Now, M is the magnitude of the gradient vector. It represents the strength of the pixel image. So if this value is greater than these 2, so this is the best one of all 3. So it keeps it. If it finds that one of them is greater than this pixel, then this pixel value is set to 0. Okay. Let's look at an example over here. Let's say there is an edge. This edge can be because there is some dark images here and some light, some dark pixels here and some light pixels here, or vice versa, some light and then some, some dark and then some light. Regardless, there is going to be an edge. If we look at this here, for example, there is an edge over here. If I look at computing the angle alpha for pixel P5, let's assume that P5 corresponds to alpha of 22.5. I take the 22.5 and then I use this circle over here. And then this means that it's going to be 22, let's say alpha is just like this. Let's say 18. So 18 is here. So it means that's going to be in this direction. These are the direction 1, 2, 3, 4. So this here represents a horizontal angle. So that's basically it. So I need to look at which 2 pixels. I need to look at pixel P2 and pixel P8. If P5 has M more than the M of P2 and P8, then it stays as is. Otherwise, it's set to 0. Okay. Hopefully that's clear. So that's the gradient magnitude, and that's the output from step 3, which is the non-maxima suppression stage. You will notice the big thing here is that the thinning that happens. You see this edge here? That's all thinned over here. All these big, thinned over here. Very, very thick edges. All of these are big edge candidate pixels. Then they are thinned over here. Why they are like this? Because we're using first order derivative and first order derivative, if you recall, always have thick edges. And then use double thresholding and connectivity analysis. So we use a threshold to remove the weak edges. We will have actually two thresholds, T high and T low, okay? And we will have an image that's applied to a T high. So we have an image that's thresholded by T high, and then we will start from T high and start following a chain of connected edge pixels until we reach another T high. And that's done by going through the T low points. So we will have points that are detected by T high, and there is points detected by T low. If I can go from one T high point to another T high point using the T low, then that's all edge points and they become part of the output. If I can't go from a T high to another T high using the T low points, then basically these points are not on an edge and they are removed. Okay, so that's called hysteresis thresholding. So basically the output will be from step 3, the non-maxima suppression, into T4. You will see a lot of the weak edges here are all gone. Only the strong edges remain, and that's the end of the algorithm. If you look at this here as a comparison for the different algorithms we studied so far for edge detection. So that's the original image. Okay. This here is using the gradient vector. Okay. This is here used the Marr-Hildreth edge detection with the approximation of difference of Gaussian, and that's using the COSC edge detector. The big thing that you notice is the following. These are thick edges, so that's just gradient image. A lot of discontinuity over here, so that's Marr-Hildreth. Someone will tell me, okay, so why is this Marr-Hildreth and it's not just Laplacian of Gaussian? Because it doesn't have double edges. The Marr-Hildreth gets rid of the double edges and just keeps one pixel edge based on a second order derivative. And how do you know that this is the COSC edge detection? Because you see over here, there is a connectivity that's happening over here that managed to connect this area together. And that's the hysteresis analysis and connectivity analysis we talked about. Okay. Let's look at COSC edge detection with different scales, again, for the applying the Gaussian at the beginning. Again, if we apply sigma that's small, we will get a lot of edges. Sigma equals 3 gets us this, sigma equals 6 gives us this, and sigma equals 10 gives us this. Yeah. So again, with the effect of the Gaussian and making the sigma larger, what happens is that the smoothing becomes stronger, and then only strong edges survive. This is just, again, another comparison of the different techniques with Sobel, Laplacian of Gaussian, and COSC for the circuit image that we talked about a few slides back. And you will see that the COSC by far is the best actual representation of what's happening. If we look at the Laplacian of Gaussian versus COSC, the Laplacian of Gaussian, if you recall, has the bumpy corners, whereas the COSC edge detection doesn't have that effect. This is a summary of the MATLAB functions that we've talked about in this lecture. So I hope that you will be able to look at this, and actually I want you to try some of these examples on MATLAB by yourself and play with the different values. so you can get a better understanding of it. In the assignment next week, actually, you will have to implement some of the things that we talked about here manually. So you actually have to write using basic programming functions, implementation for some of these functions. As usual, if you have any questions, just email me. I'll be happy to meet with you and talk. Okay, thank you, and have a great weekend.